right. Looks like everything is working the way it should be. Okay, so today we are going to finish up 5-5 and hopefully 5-6 as well. And this is our U substitution. So let's say, for example, we wanted to integrate from -1 to 0, -5x times x squared minus 1 to the 4th power with respect to x. Okay. Now, when you have a definite integral, these steps are exactly the same as if you had an indefinite integral, no upper and lower limits. But it's just one thing you have to be careful of, and I'll show you that in 1 second, as soon as we reach that part. Okay, so I'm just going to factor out my constant. Again, that's usually my very first move, just to make it a little simpler. Okay, and I'm going to switch these two up, only because I know that I'm going to make x squared minus 1. That's going to be my u. And when I take that derivative, it's going to give me an x. So I'm going to move that x next to that dx. So we have x squared minus 1 to the 4th power times x dx. So that's a good strategy for picking which one to make u. If you took the derivative of x, you wouldn't get x squared. So you know you wouldn't make that x your u. If you get the derivative of 2x, you'd get an x. So that's the one you'd want to make your u. Okay, so we know that x squared minus 1, that's our u. So the derivative of u is equal to 2x, which is the derivative of x squared. And the derivative of -1 is 0, so that just disappeared. So it's 2x dx. Okay, so knowing we have this x dx right here, we want to get rid of that 2, so we divide or multiply both sides by 1/2. Oops. So we have 1/2 du, those 2's cancel each other out, is equal to x dx. Okay. So this x squared minus 1 to the 4th power, that becomes u to the 4th power. And this x dx becomes 1/2 du. Or you can say du over 2, completely up to you. But I just like to put 1/2 du. So that brings us to -5 times the integral from -1 to 0. Instead of x squared minus 1, we just replace that with u to the 4th power. Excuse me. And that x dx, we replace that with 1/2 times du. So if we take that 1/2 and just factor that constant right out to the front, you can just say -5 over 2, but I'll just write it as -5 times 1/2 for right now, times the integral from -1 to 0 of u to the 4th power du. Okay, so once this all matches up, just remember it's the exact same. The goal is to get it in the form of the integral of x to the power 4 dx. And we know that's x to the 5th power over 5. Doing the same thing here, once we get it all in the form that we need it to be in, we can just take the integral of this after we simplify the negative 5 times 1/2 and make that negative 5 over 2. We can just rewrite this interval as u to the 5th power over 5. Okay. Now remember, your upper and lower limit, that's the upper and lower limit for your x value. So that's from x equals -1 to x equals 0. So as long as it's still in the u form, you don't want to plug in your x values. It's probably the most common mistake. Okay, so those two 5s cancel each other out. So we're left with -1/2 times u to the 5th power from x equals -1 to x equals 0. Okay. So we do not want to plug in those x values for u. So all we have to do in order to be able to plug those in is just replace the u with our x function. So we just replace u. And in this case, u is equal to x squared minus 1. So that becomes x squared minus 1 to the 5th power. We have -1/2 times x squared minus 1 to the 5th power. And that's from x is equal to -1 to x is equal to 0. Okay, so you want to be careful, even though it's just going off instinct. It looks like, okay, now that I have it here, I just plug that in. You don't want to do that until you replace your u with your x function. And once you replace it, now you can apply the fundamental theorem. Make that a little bit neater. Okay, which means we plug in our upper bound. So we have -1/2 times 0 squared minus 1 to the 5th power. Minus, now we plug in our lower bound. So that's -1/2 times -1 squared minus 1 to the 5th power. Let me move this up just, there we go, so you can see the bottom. Okay, so -1 squared is just +1, and 1 minus 1 is 0, so 0 times anything is just 0, so that just cancels out. And this -1/2 times 0 is just 0, so that just cancels out. Oh, not the whole thing. I wrote that a little too long. Just that particular term. Okay, so that leaves us with -1/2 times -1 to the 5th power, which is -1. So I'll just write -1 to the 5th power, which gives us -1/2 times -1, which is +1/2. Okay, so any questions on that one? All right, leave that up there for a little bit. Now for this section on down, this is one method to do it, and it works just fine. There's also another method if you want to leave it with the U there. And you can pick whichever method you like best. It's completely up to you. But I'll show you both. So method number 2. And we'll start just where it says -1/2 of u to the 5th power from x equals -1 to x equals 0. Okay. So we know that u is equal to x squared minus 1. Or you can write it as u of x equals x squared minus 1. Okay. So we know we can't plug in x equals -1 or x equals 0, but what we can do is rewrite our upper and lower limits to become the upper and lower limits for the function of u. So since our lower limit is -1, we just have to replace that with u of -1. And since our upper limit is 0, we just replace that with u of 0. Okay, so u of 0, since u of x is x squared minus 1, u of 0 is just 0 squared minus 1, which is -1. And u of -1 is equal to -1 squared minus 1, which gives us 0. So now our upper and lower bound, we can just rewrite that as -1/2 times u to the 5th power from u is equal to 0 to -1. Since that's our new upper and lower bound. So we know u of 0 is equal to -1, and u of -1 is equal to 0. So now we can just go ahead and use the fundamental theorem. So that gives us -1/2 times -1 to the 5th power minus -1/2 times 0 to the 5th power. Where that, once again, just disappears because it becomes 0. And -1 to the 5th power is -1, so -1 times -1/2 is just 1/2. So you get the same answer either way. It's just a matter of picking the one that you prefer. Like I said, I'm okay with either one. So I just personally prefer the first one. No particular reason for it. Okay, so any questions on that one? All right. Now, the next one, it's going to be a problem that you're probably going to run across, and I'll show you how to handle it. What if we evaluate the integral of x times x minus 6 to the 6th power with respect to x? Okay. So what if we let our u equal x minus 6. It means our derivative of u is equal to the derivative of x is just 1, so 1 minus 0 is just 1. So the derivative of u is just equal to dx, or 1 dx. Okay. Now, the only problem with that is that if we take our integral and just switch those around, say x minus 6 to the 6th power times x dx. Okay, this x minus 6 to the 6th power, that's no problem because we can just write that as u to the 6th power. But du is equal to dx. So that dx just becomes our du. But we still have that x there. So we wouldn't be able to integrate as long as that x is still hanging around. We have to rewrite it as strictly an integral of the, I guess you could call it the variable u. Okay. So if this happens, all you have to do, once again, we're going to let, I'll just write to fix this. We're going to let u equal x minus 6. And du is still dx. Okay, so we're still going to use these two, but if we take our u is equal to x minus 6 and add 6 to both sides, we can go ahead and cross that out. That'll give us x is equal to u plus 6. So that means we can take this integral of x minus 6 to the 6th power times x dx. Our u is still u to the 6th power. And our dx is still du. But now we can rewrite this x and just make that u plus 6. So we have strictly a function of u. I'll put little parentheses around that just to make sure. So each and every part of that integral has to be in some way a function of u for this to work. So we just got rid of that x by replacing that with u plus 6. Okay. So does that make sense? Okay. So now if we rewrite it, we have the integral that x minus 6 to the 6 is now u to the 6th power. That x is times u plus 6, and that dx is du. So if we distribute that u to the 6th power, that gives us the integral of u to the 6th times u is u to the 7th power, plus u to the 6th power times 6 is 6u to the 6th power. So clean up that 6 a little bit. There we go, du. Okay, so now we can integrate like we normally would because everything matches up to be the independent variable u. So the integral of u to the 7th power is u to the 8th power over 8 plus 6 times the integral of u to the 6th power, which is u to the 7th power over 7. And since there are no upper and lower limits, we're going to add on our plus c. Okay, so now all we have to do is just replace our u. So that 1 over 8, we can factor that out to the front. So we have 1 over 8. Instead of u to the 8th power, that's x minus 6 to the 8th power. Plus, factor that 1 over 7 out, that's 6 over 7. And instead of u to the 7th power, that's just x minus 6 to the 7th power plus c. All right, any questions on that one? All right. Okay, so now let's look at u substitution. Integration. Uh-oh. For trig functions. Okay, so let's say, for example, we want to find the integral of negative 11 times t to the 7th power times cosine of t to the 8th power dt. Okay. Now for this one, the goal is to put it in the form of the integral of cosine of u du. Okay, that's our goal before we can do anything else. Okay, so that means we're going to have to let u equal t to the power of 8. And we're going to need that, so let's mark that, which means our du is equal to the derivative of t to the 8th power, so we bring down the 8 times t to the power of 8 minus 1, so that's to the 7th power dt. So if we go ahead and divide both sides by 8, we get 1 over 8 du is equal to t to the 7th power dt. Okay. So again, I always start off with factoring out my constant and switch and put the value, the factor that's going to be with the dt next to it. And again, you don't have to do this step. It's completely up to you. So negative 11 times the integral. So we'll make that cosine of t to the 8th power times t to the 7th power dt. So all I did was switch those two around. So this will just become cosine of u. And t to the 7th power dt, that becomes 1 over 8 du. So again, that 1 over 8, we can just factor that right out to the front. So that becomes negative 11. You can put negative 11 over 8, but I'll just write it as negative 11 times 1 over 8 for this step, times the integral of cosine of u. And since we factored that 1 over 8, we're just left with the du. Okay, so for this one, all you have to do is remember that the integral, we'll make that integral a little bit neater than that. That the integral of cosine of u, cosine of x, rather, dx, is equal to sine of x. So the integral of cosine of u, we can just rewrite that as negative 11 over 8. And this integral of cosine of u is just sine of u. So that's times sine of u. And since we don't have an upper and lower limit, we know we have to add our plus c. And the last step is just replace our u. So that means our final answer is negative 11 over 8 times sine of t to the 8th power plus c. All right, any questions on that one? All right. So let's say if we wanted to find the integral of negative 12 times x squared times sine of x to the 3rd power with respect to x. Okay, so again, for this one, the goal is to put it in the integral of sine of u du form. Okay, so that means we're going to let our u equal x to the 3rd power. And we're going to need that a little later, so we'll go ahead and highlight it. Which means our du is equal to the derivative of u, so that's 3x squared with respect to x. So if we divide both sides by 3, we get 1/3 du is equal to x squared dx. And we're going to need that, so we'll highlight that one too. Okay, so again, I'm just going to take my factor, a negative 12, and factor it out to the front. So we have negative 12 times the integral. I'm going to switch these two around. So that's sine of x to the 3rd power times x squared dx. Okay, so we know that this will give us sine of u, because our u is equal to x to the 3rd power. And that x squared dx, that will give us our 1/3 du. So if we take this 1/3 and just factor it out to the front, that will give us -12 times 1/3 times the integral of sine of u du. Okay, and since we know that, got my integral, the integral of sine of x dx is equal to negative cosine of x plus c. We know this integral will just give us, we have -12 times 1/3. We can just go ahead and replace that with -4. And the integral of sine of u du is negative cosine of u plus c. That's times negative cosine of u plus c. Okay, so all we want to do is we want to get it into the same form as our integrals with respect to x, but we just want to do it with respect to u. So as long as we match it up, the integral will be exactly the same, just u instead of x. Okay, so now for this one, we just have to simplify and replace u. And by simplify, we just have to notice that -4 times negative cosine, negative times negative is positive. So that just becomes +4. And the cosine of u, that becomes cosine of x to the third power. So I times cosine of x to the third power plus c. All right, so any questions on that one? All right. Okay, now I tried to show you examples of any tricky ones I think you might run across, and this one might qualify as a tricky one, but we'll go over it just in case. So let's say if we want the integral of 17 times cosine of t to the fourth power times sine of t with respect to t. And it's not really tricky, it's just a certain way you have to approach it. Okay, so for this one, or any problem like this, let me make that 4 a little higher up and smaller. Here we go. For this one, you just want to remember that you can rewrite that cosine, fourth cosine of t, that's the same as saying cosine of t to the fourth power. Okay, so if we rewrite it, again, I'm just going to factor out that 17 times the integral and rewrite it as cosine of t to the fourth power times sine of t dt. Okay, so now we can just let u equal cosine of t. And the derivative of cosine is negative sine, so that's negative sine of t dt. Okay, but we don't want negative sign, we want positive sign. So if we divide both sides by -1 or multiply both sides by -1, up to you. Those two will cancel out. So that gives us -1 du, or you can just put negative du, is equal to sine of t dt. And we kind of separate that a little bit so it's not running into there. Okay, so we know that this will just become u to the fourth power. And sine of t dt would just become -1 du, or -1 times du. So if we get that -1 and just factor it out to the front, we can have 17 times -1 times the integral of u to the fourth power du. And this part, I'll put a little barrier around it to separate it. Okay, so 17 times -1 is just -17. And since we know that if we had the integral of x to the fourth power dx, that would just equal x to the fifth power over 5 plus c. The integral of u to the fourth power du is just u to the fifth power over 5 plus c. So if we factor out this 1 over 5, that'll give us -17 over 5. Times u to the fifth power plus c. Okay, so once we have it all done, the very last step is just to replace the u. So since u is equal to cosine of t, we can just rewrite this as -17 over 5 times cosine of t to the fifth power plus c. Or you can write it in the more traditional form of -17 over 5 times cosine of t to the fifth power plus c. Again, I'm not 100% positive about this form on Newton, so if you put it in this one, it should work, but if you put it in and it doesn't, then I would try that form. All right, so any questions on that one? Okay, so let's try a definite integral. So what if we wanted to know what is the value of the integral from pi over 2 to pi of 3 times cosine of t And I'm trying to see if I'll run out of room. I should be able to get it. Times sine of t to the 5th power with respect to t. Okay, so remember you can rewrite this. So that'll give you the integral from pi over 2 to pi. That 3, we can factor that right on out to the front. And we can switch these up and rewrite that sine of t to the 5th power as sine of t to the 5th power times cosine of t dt. And make that 5 a little bit smaller. There we go. Okay, so now we can just let u equal sine of t. Which we will need a little later, so we will highlight that. And our derivative of sine is cosine, so our du is equal to cosine of t with respect to t. Well, there are no coefficients other than 1, so you don't have to multiply or divide it by anything, so we can just leave it just like that. And I probably should have moved that over there because I wanted to have room to write under here. Well, I'll squeeze it under here. Okay, so this will give us u to the 5th power. And this will give us du. Had just enough room. Okay, now we have 3 times the integral from pi over 2 to pi of u to the 5th power du. And make that pi a little bit neater than that. There we go. Okay, so that's 3 times the integral of u to the 5th power is u to the 6th power over 6. And we don't put the plus c because we have a definite integral. So that's from pi over 2, or you can put from t equals pi over 2 to remind you not to plug it in, to t equals pi. Okay, so we can just factor out that 6. So that gives us 3 over 6 times u to the 6th power from t equals pi over 2 to t equals pi. So to plug it in, we can either find u of pi over 2 and u of pi, or we can just replace this with sine of t. Okay. And again, my preferred method is just to go ahead and replace it. Okay, so that 3 over 6, we can just simplify that to 1/2. And that u to the 6th power, we can just make that sine of t to the 6th power from t equals pi over 2 to t equals pi. And I purposely leave it in this form when I'm going to plug in the values. It just makes it a little easier for me instead of rewriting it in this form up here. So for some reason for me, just in that form makes it a little tricky sometimes. So I just leave it in this form. So we have 1/2, and now we can apply the fundamental theorem. Oops. So we plug in our upper bound. Okay, so that's sine of pi to the 6th power minus, now we plug in our lower bound. So that's sine of pi over 2 to the 6th power. Okay, so sine of pi is equal to 0. So that's just equal to 0 to the 6th power, or just 0. And sine of pi over 2 is 1. So this equals 1. So it gives us 1/2. And you don't have to write out this step if you don't want to, but I just usually do it. Times 0 minus 1 to the 6th power, which is 1. So 1/2 times -1 is just 1/2. Well, -1/2. All right, so any questions on that one? Okay, so again, the process for each one is pretty similar, or they are pretty similar, so you'll probably make adjustments to the process to fit how you want to do it, but whichever way you want to do it, and perfectly okay with me, as long as you're not breaking any math rules. Excuse me. Okay, so now we're going to go ahead and start section 5.6. Okay, so we have section 5.6, and that's U substitution for logarithmic and exponential functions. Okay. And again, for these, you don't have anything new to remember. All you have to do is take your antiderivative with respect to x and replace the x with u. So the antiderivative of du over u is just the natural log of u plus c, where the integral of dx over x is just the natural log of x plus c. We know that the integral of e to the power of u du is equal to e to the power of u plus c, because we know that the integral of e to the power of x dx is e to the power of x plus c. So again, just replace x with u. It's the exact same formula. And if we have the integral a to the power of u du, that's equal to a to the power of u divided by the natural log of a plus c. And the integral of log base a of u du is equal to u times the natural log of u minus 1 all over the natural log of a plus c. Right. So let's say if we wanted to find the integral of 4 times t to the 4th power times e to the power of 6t to the 5th power with respect to t. Okay, so for this one, our goal is to put it in the integral of e to the power of u du form. Okay, so again, I take my constant and just move it out to the front. And just switch these two around. So we have e to the power of 6t to the 5th power times t to the 4th power dt. That means we're going to have to let our u equal 6t to the 5th power. Which means our derivative of u is equal to 6 times the derivative of t to the 5th power. So if we bring down the 5, that 6 times 5 will give us 30, times t to the power of 5 minus 1, which is 4, with respect to t. So if we divide both sides by 30, we end up with 1 over 30 du is equal to t to the 4th power dt. Okay, which works out perfectly because we can replace e to the power of 6t to the 5th power. We can just replace that to e to the power of u. And that t to the 4th power dt, we can replace that with 1 over 30 du. Make that 30 a little bit neater. There we go. So if we get this 1 over 30 and factor it out to the front, that gives us 4 times 1 over 30 times the integral of e to the power of u du. Okay, and that 4 times 1 over 30, we can just make that 4 over 30. And the integral of e to the power of u du is just e to the power of u plus c. now all we have to do is simplify and replace u. So that 4 over 30, we can simplify that to 2/15. And that e to the power of u will just become e to the power, here we go, of 6t to the 5th power. And make that 5 a little neater than that. Here we go. Plus c. All right, so any questions on that one? All right. Let's say for this one, we wanted to evaluate the integral from -2 to -1 of 4 times e to the power of 2t minus 4 with respect to t. And we want to leave the answer in the exact form. This is just a fancy way of saying we don't want a decimal answer. Okay, so again, first thing I always do, factor out that constant. So we have 4 times the integral from -2 to -1 of e to the power of 2t minus 4 with respect to t. Okay, so again, we know that our goal is to put it in the integral of e to the power of u du form. So that means we're going to let u equal 2t minus 4. And we know the derivative of u is equal to the derivative of 2t is just 2. And the derivative of -4 is 0, so that disappears. So that's just 2 with respect to t. Or if we divide both sides by 2, we have 1/2 du is equal to our dt. Which means we can go ahead and rewrite this as e to the power of u. And our dt, we can rewrite that as 1/2 du. So if we take that 1/2 and factor it out to the front, then that will give us 4 times 1/2 times the integral from -2 to -1 of e to the power of u du. Okay. So that 4 times 1/2, you can just replace that with 2. That integral of e to the power of u du is just e to the power of u It's a definite integral, so we don't need the plus c since we have an upper and lower bound. But remember, this is from t equals -2 to t equals -1. Okay, so now we just go ahead and replace u, so we can plug in our t values. So this just becomes 2 times e to the power of 2t minus 4 from t equals -2 to t equals -1. And now we can do the fundamental theorem. So we go ahead and plug in our upper bound. That's 2 times e to the power of 2 times -1 minus 4 minus, now we go ahead and plug in our lower bound, e to the power of 2 times -2 minus 4. Let's make that 4 a little bit neater than that. Okay, so that gives us 2 times e to the power, 2 times -1 is -2, so -2 minus 4 is -6, minus 2 times -2 is -4, so -4 minus 4 is -8, so e to the power of -8. Okay, so this is the exact form, but again, I'm not sure how Newton would feel about negative exponents, so you can rewrite it as 2 times 1 over e to the power of 6 minus 1 over e to the power of 8. All right, any questions on that one? All right. Okay, so what if we wanted to find the integral of 18 times e to the power of 3x times the square root of 6 plus e to the power of 3x with respect to x? Okay, so again, most root functions, the first thing I would always try is just to rewrite it in exponential form. So the square root of 6 plus e to the power of 3x, we can rewrite that as 6 plus e to the power of 3x to the 1/2 power. Okay, so again, I'm going to get my constant and move it out to the front just because. Then I'm going to switch these two around, but I'm going to write this square root in its exponential form. So it's times the integral of 6 plus e to the power of 3x to the 1/2 power times e to the power of 3x. dx. Let's clean up that 6 a little bit. There we go. Okay, so remember the goal for this one, even though it has an e to the power of 3x, that's in a 1/2 or square root. So here it's just u to the power of n du. So it wouldn't actually be a e to the power of u du form for this one. Okay. So we're going to let our u equal 6 plus e to the power of 3x. And we're going to need that, so we'll highlight that, which means our derivative of u is equal to, the derivative of 6 is just 0, so that disappears. The derivative of e to the power of 3x is e to the power of 3x times the derivative of 3x, which is 3. So it's 3 times e to the power of 3x with respect to x. Draw a little arrow here. So if we I can say multiply both sides by 1/3 or divide both sides by 3, we get 1/3 du is equal to e to the power of 3x dx. Okay, so we see that this will just become u to the 1/2 power. And e to the power of 3x dx will become 1/3 du. So again, we take that 1/3 and we can factor that right on out to the front. So it gives us 18 times 1/3 times the integral of u to the 1/2 power du. Okay, so 18 times 1/3 is just 18 over 3, which we can just make equal to 6. And the integral of u to the 1/2 power is u to the 1/2 plus 1 power over 1/2 plus 1 plus c. Okay, so 1/2 plus 1, we can just say 1/2 plus 2 over 2, which is u to the 3/2 power divided by 3/2. And leave a little bit of room after that because we want to get rid of that 3/2 in the denominator. Okay, so we multiply the numerator and denominator by the reciprocal of the denominator. So that 3 over 2, we're going to multiply it by 2 over 3 over 2 over 3. So if we multiply our denominator, 3/2 times 2 over 3 is just 6 over 6, which equals 1. So those two cancel each other out. And this 2/3 right here, we can just factor that right onto the front. So we have 6 times 2/3 times u to the 3/2 power plus c. So we just simplify and replace u. Okay, so 6 2/3, that's just 12 divided by 3, so we can just replace that with 4. And u to the 3/2 power, that would just become 6 plus e to the power of 3x to the 3/2 power plus c. All right, any questions on that one? Okay. So what if we wanted to integrate 11 times log base 14 of t with respect to t? Okay. And honestly, the log integrals are probably the easiest because you're just plugging stuff in. So we just have to remember that the integral of log base a of u du is equal to u times the natural log of the absolute value of u minus 1, all that divided by the natural log of a plus c. Okay, so if we rewrite it, take our constant, factor that out to the front. So 11 times the integral of log of base 14 of t dt. Okay, so if we match these bases up, we see that a is just equal to 14. Oh, why did I put 4 there? Of t dt. I think I had 14 on the brain and just put 4 there for some odd reason. And if we match this up again, we can see that u is equal to t. So that means if u is equal to t, then our derivative of u is equal to 1 dt or just dt. Okay, so if we just match this up, all we have to do is plug in the u's and the a's into our formula, because we know that this is just 11 times the integral of log base a of t. Oh, I guess you could say of t or u. I'll put u in its t place. Du, we know that is u times the natural log of the absolute value of u minus 1 divided by the natural log of a plus c. So if we just plug in those values, and you don't have to repeat that if you don't want to. I just rewrote it just because. That u, we're going to replace that with t. Times the natural log of u, we're going to replace that with the natural log of t. Minus 1 divided by the natural log of a, just replace that with the natural log of 14, plus c. Okay. Now the absolute value here, it really isn't necessary only because we know that an argument would have to be greater than 0. So we already know this is positive. So they might want the absolute value. They might accept parentheses. Like I said, with Newton, I can't really say how it's programmed. So but I would probably put the absolute value just to be on the safe side. So you don't have to go back and change it if they don't accept it. All right. So any questions on that one? Excuse me. All right. So what if we want to find the integral of 9 divided by t minus 5 with respect to t? Okay, so if we rewrite this, just get that 9 and bring it out to the front, times the integral, that dt, we can just move that right up there in the numerator. So we can say dt divided by t minus 5. Now you don't have to, this just puts it into a more familiar form. Actually, what I'll do is I'll write both, just so you don't have to write both, I'm just going to do it. So 1 over t minus 5 dt, or say 9 times the integral of dt divided by t minus 5. So I'll just put one or the other. Again, you can use whichever form you're more comfortable with. Okay, so what if we let u equal t minus 5? Okay, well, that means the derivative of u is equal to the derivative of t is just 1, minus the derivative of 5, which is 0. So 1 minus 0 is 1. So this is 1 dt, or you can just put dt. So if you rewrite this, this is just 9 times the integral of dt. We can replace that with du. Divided by t minus 5, we can just replace that with u. Okay, so this one, we can see that it's in the form of the integral of du over u is equal to the integral of 1 over u du, which is the same thing. Just basically both forms of this one right here. which we can just rewrite as the natural log of u plus c. Okay, so up here, I just rewrote it in both of the forms that I wrote this problem in. So depending on which form you want to keep it in, they're both the same. Okay, so this will just become 9, and the integral of du over u will just become the natural log of u plus c. So now if we just go ahead and replace our u, you see that our final answer will be 9 times the natural log of u. That becomes the natural log of t minus 5 plus c. Okay, now with this one, you would have to have the absolute value because there's nothing in our original integral that would suggest that t minus 5 is always going to be positive. So with this one, you would need the absolute value. That's why I say I would put the absolute value on all of them just to make it habit. All right, any questions on that one? All right. Okay, so for this one, let's say if we wanted to find the integral of 9t squared plus 16t to the 5th power divided by 9t to the 3rd power plus 8t to the 6th power with respect to t. Okay, so with this one, the first thing I would look at would be my exponents. And if you notice, the exponents of the numerator are one less than the ones in the denominator. So to me, that would suggest a natural log solution. So that would be the first thing I would try. So what if we let u equal to our denominator? It's 9t to the 3rd power plus 8t to the 6th power. Okay. And the reason the numerator exponent is being one less than the denominator exponent gives me a hint is because when I take the derivative, each one of those exponents are going to go down by 1. Okay, so if we bring down the 3, that gives us 9 times 3, which is 27t squared, plus 8t to the 6th power. Bring down the 6, 8 times 6 is 48, t to the 5th power with respect to t. So we can see there it doesn't match our numerator. But if we factor out a 3, it will. So if we factor out that 3, we get du is equal to 3. So now that 27t squared becomes 9t squared. And that plus 48t to the fifth becomes plus 16t to the fifth power with respect to t. Okay, so it might not match it immediately, but if you factor out some greatest common factor, you can usually make it match up. So if we divide both sides by 3, we get 1/3 du is equal to 9t squared plus 16t to the fifth power with respect to t. So we know we're going to use that. So we'll highlight that one. Okay, so we know that our integral of 9t squared plus 16t to the fifth power divided by 9t to the third power plus 8t to the sixth power. And the du, you can leave it on the right. Me, I just always like to move it up top. I mean, not du, dt. Just move the dt up top. Okay, so if we match this up, we have the integral 9t squared plus 16t to the fifth power dt. We can replace that with 1/3 du. So we have 1/3 du divided by 9t to the third power plus 8t to the sixth power. We can just replace that with u. Okay, so if we get that 1/3 and just factor it right out to the front, that's going to equals 1/3 times the integral of du over u. Well, we know the integral of du over u is the natural log of u. So that's equal to 1/3 times the natural log of u plus c. So all we have to do is replace our u. And that gives us 1/3 times the natural log of u, so that's times the natural log of 9t to the third power plus 8t to the sixth power plus c. All right, any questions on that one? Okay, now sometimes you will have this du over u to where all you have to do is factor out a greatest common factor and then it'll become nice and neat. But other times it's not always nice and neat. So you might have to approach it in a slightly different way. Okay, so what if we have the integral of 30t plus 54t to the third power divided by 10t squared plus 9t to the fourth power with respect to t. Okay, so again, we can pretty much see that we're going to have a natural log answer because the exponents are one less in the numerator. So we're going to let our u equal our denominator, which is 10t squared plus 9t to the fourth power. So if we find our derivative of u, that's equal to, we bring down the 2 for the 10t squared. 10 times 2 is 20, times t to the power of 2 minus 1, which is just t, plus we bring down the 4. 9 times 4 is 36, so we have 36t to the third power, and that's with respect to t. Okay, so we can see here we can't factor out any value to magically make 20 equal 30 and 36 equal 54. Okay, but we can still solve it. All we have to do is realize that this should be 20t, and this should be 54t to the third. Uh-oh. Okay, so we know what it should be in order for our function or integral to be transformed into one that we can make a natural log answer. Okay, so that means we have to turn that 20 into 30. Okay, so all we have to do is find out, let me move this over a little more to make sure we have enough room. 20 times what number would make it equal to 30? Well, if you divide both sides by 20, you have x is equal to 30 divided by 20. If we simplify that, x is equal to 3/2. So we know that x times 3/2 will give us 30. And let's see if it works for the other one. We know that 36 times some number has to equal 54. So if it's 3/2 also, we're good. So if we divide both sides by 36, we have x is equal to 54 divided by 36. So if we divide both of those by 18, or multiply by 1 over 18, or you can just say divide by 18 and divide by 18, we see that we get x is equal to 3/2. So all we have to do with that is multiply both sides of the du by 3/2. So we end up with 3 over 2 du is equal to 3 over 2 times 20t plus 36t to the third power with respect to t. Okay, so if we distribute that 3 over 2, and this is just a double check to make sure it's actually going to give us what we want it to give us. That means that 3 over 2 du is equal to 3 over 2 times 20 would give us 60 divided by 2, which is 30. So that's 30t plus 36 times 3 divided by 2 will give us 54. T to the third power, dt. Okay, so it all matches up. So that means that we can take our integral of 30t plus 54t to the third power divided by 10t squared plus 9t to the fourth power. And again, I'll just move my dt up to the top just to match the form. Well, that's equal to the integral 30t plus 54t to the third power dt. We can just replace that with 3/2 du. Divided by 10t squared plus 9t to the fourth power. We can just replace that with u. So if we get that 3/2 and just factor it right out to the front, and that gives us 3/2 times the integral of du over u. And we know that the integral of du over u, that gives us 3/2 times the natural log of u plus c. Okay, so now the last step, all we have to do is replace u. So that gives us 3/2 times the natural log of 10t squared plus 9t to the fourth power plus c. Okay, and with this one, you actually wouldn't need the absolute value only because your exponents or your variable exponents are all even. So that means if you plug in a negative value, you'll still get a positive number. If you plug in a positive value, you still get a positive number. So when you have all positive exponents and all plus signs, you don't really need the absolute value. But again, I always put it just out of habit. All right. Oops. Okay, so let's say we want to find the integral from 1 to 2 of 3x plus 4x to the third power divided by 3x squared plus 2x to the fourth power with respect to x, and we want to have that in an exact answer. So again, first thing I would notice, the exponents of our denominator, or the numerator, is 1 less than the exponents from the denominator. So again, you can expect a natural log answer. So that's when we let u equal our denominator. And move that over a little bit. So let u equal 3x squared plus 2x to the fourth power. Which means our derivative of u, highlight that because we know we're going to need it. Our derivative of u is just equal to, we bring down the 2, 3 times 2 is 6. So 6 times x to the power of 2 minus 1 is just 6x. Plus, we have 2 times x to the power of 4. The derivative of x to the power of 4, we can just bring down the 4. That makes it 8 times x to the power of 4 minus 1, which is 3. And that is with respect to x. Okay, so we can see here that 6x should be 3 and 8x to the third should be 4x to the third. We can just factor out 1/2. But just for practice, we're going to do the steps where we match it all up. Okay, so with this one, we see that it should be 3x. And with this one, it should be 4x to the third power. Like I said, if you can look at it and see what needs to be factored out, definitely go through that. This is simply for practicing that last step. Okay, so since this should be 3x, we want to find what number times 6, and we can't use x, so let's say 6y, would make that equal to 3. So if we divide both sides by 6, we have y is equal to 3 over 6. Simplify that, we have y is equal to 1/2. Same thing here. It should be 4x to the third power. So what number can we multiply by 8 to make it 4x to the third power? So we'll say 8 times y equals 4. So if we divide both sides by 8, we have y is equal to 4 over 8, or just y is equal to 1/2. So again, these two match up, and we can just multiply both sides of the du by 1/2. Okay. And again, this is only necessary when you can't look at it and tell what you need to factor out of both of them to make them match. Even though we could look and tell, yeah, we just factor out a 1/2. So that means your 1/2 du is equal to 1/2 times 6x plus 8x to the third power with respect to x. That'll make that du a little bit neater. Multiply du by 1/2, just to make sure that's clear. There we go. And make that a little neater. Here. Okay, so if we distribute that 1/2, we have 1/2 du is equal to 1/2 times 6 is 3. So that gives us 3x. Plus 1/2 times 8 is 4. It gives 4x to the third power dx. Okay, so that means that we can take our integral from 1 to 2 of 3x plus 4x to the third power divided by 3x squared plus 2x to the fourth power. And again, that dx, I'm going to move it up top. Okay, and if we match it up, we can see that we have the integral from 1 to 2, that 3x plus 4x to the third power dx. We can just replace that with 1/2 du. Divided by 3x squared plus 2x to the fourth power. We can just replace that with u. So once again, we're going to factor that coefficient right out to the front. So that's just 1/2 times the integral of du over u from 1 to 2. Okay, so we know the integral of du over u is just natural log of u. That's going to equal 1/2 times the natural log of u from 1 to 2. But remember, this is still from x is equal to 1 to x is equal to 2. So you don't want to just plug it in and get natural log of 2 minus natural log of 1. That would have been the incorrect answer. So it's still the x values. So before you plug them in, you have to replace your u. So that would give you 1/2. And instead of the natural log of u, that would give us the natural log of 3x squared plus 2x to the fourth power. And that is from x is equal to 1 to x is equal to 2. Okay. So now we can apply the fundamental theorem. So I'm just going to move this over to make sure we have enough room. So that's 1/2 times. So we plug in our upper bound. That's the natural log of 3 times 2 squared plus 2 times 2 to the fourth power minus, plug in our lower bound, the natural log. Oh, forgot my other absolute value symbol. There we go. The natural log of 3 times 1 squared plus 2 times 1 to the fourth power. Okay, so if we simplify that, we have 1/2 times the natural log. We have 2 squared, which is 4. 4 times 3 is 12. Plus 2 to the fourth power. 2 times 2 is 4. 4 times 2 is 16. 16 times 2 is 32. 32 plus 12 gives us 44. Minus the natural log of 3 times 1 is 3 plus 2 times 1 is 2, so minus the natural log of 5. And we don't really need absolute values for 5 and 44 because they are positive, but again, I always do that strictly out of habit. All right, so any questions on that one? Again, most of these are pretty straightforward, but when you get to some of these where the integral just doesn't jump right out at you, just look for little hints like the variable exponents going down by 1 each. Then that'll tell you which direction you can kind of go to. right. So now we are going to start section 5.7, which covers inverse trig functions or integrals that result in inverse trig functions. Okay. Now, these are a little bit tricky, but only because you have to be able to kind of immediately recognize the pattern. And that usually involves either having the inverse trig functions within view so you can use them, or memorizing them. So, like I said, just a little bit tricky on these until you get used to them or have the integrals memorized, then you'll be okay. But at first, it's a little bit tricky. Okay, so we know that the integral of du over the square root of a squared minus u squared is equal to sine inverse of u over a plus c. And we have the integral of du over the absolute value of u times the square root of u squared minus a squared. We know that's equal to 1 over a times secant inverse of u over a plus c. And we know the integral of du over a squared plus u squared is equal to 1 over a times tangent inverse of u over a plus c. Okay, so if you notice, I'm just going to stop at these three. And that's because the negative inverse of du over the square root of a squared minus u squared, that's cosine inverse of u over a plus c. Or you can just write that as -1 times the sine inverse, times the integral of du over the square root of a squared minus u squared, which is just the negative sine inverse of u over a plus c. Okay, so if we take this one that results in secant inverse and we put a -1 next to it, so we don't even need the -1, just the negative will work. So the negative of du over the absolute value of u times the square root of u squared minus a squared, that's going to equal 1 over a times cosecant inverse of u over a plus c. Okay. Or we could just say negative of the integral that results in the secant inverse. We could just say negative 1 over a secant inverse of u over a plus c. Same thing if we put a negative on the integral of du over a squared plus u squared. We multiply both sides by negative 1. And that gives us the integral, the negative integral of du over a squared plus u squared, which is equal to 1 over a. And instead of tangent, the negative of that is cotangent inverse of u over a plus c. Or we can just write it as the negative of 1 over a times tangent inverse of u over a plus c. Okay, so these three up here, these are the ones you use the most. But these three right here, those aren't used as often. Not saying they're never used, they're just, most people don't use them. Because if you already have these three memorized, if there's just a negative in front of here, then you might as well just put a negative in front of here also, instead of memorizing three other solutions or formulas. Okay, so these three are the usual form for it. Now with Newton, I don't know if they'll accept the cosine inverse and cosecant inverse and cotangent inverse, but I believe they, at least last time I checked, they mostly use the sine, secant, and tangent. So unless they updated it over the past month or two, they probably accept the answer in sine, secant, and tangent inverse form. I mean, you can try these. I would definitely try them if you want to. But like I said, these kind of a crapshoot. These pretty much guaranteed to be accepted. All right. Okay, so let's say, for example, we wanted to find the integral of -3 divided by the square root of 36 minus 81 x squared with respect to x. Okay, so if you look at the form of that integral, if you notice, it's really similar to, I'll put it right here, the integral of du over the square root of a squared minus u squared, which is equal to sine inverse of u over a plus c. Okay, so if we moved our dx up to the top, we'd have dx over the square root of some number minus some term we could call u. Okay, so all we have to do now that we see one that it's similar to, we just have to match them up. So we can figure out what's our u, what's our a, what's our du. So if we factor out that -3, just bring that right out to the front and move our dx up top. So that's divided by the square root of 36 minus 81 x squared. Okay, well, if you notice in our formula, you have a squared minus u squared. So we have to rewrite both of those terms as some value or some function squared. So we can just make 36 is equal to 6 squared. And that 81x squared, we can just rewrite that as 9x squared. So that means we can write that as -3 times the integral of dx over the square root, and instead of 36, we'll make that 6 squared, minus, instead of 81x squared, we'll just make it 9x squared. So 9x and that whole thing squared. Okay, so if we match it up to our formula, if we have a squared, that means in this case, a would be equal to 6. And minus 9x squared, so that means for this one, our u will equal 9x. Okay, so the only thing we have left to find is our du. So we know that if u is equal to 9x, we can use that to find du. And that means our derivative of u is equal to the derivative of 9x is just 9 with respect to x. Excuse me. So if we divide both sides by 9, we have 1 over 9 du is equal to dx. And we're going to need that, so we'll go ahead and highlight that. And our u, well, we already have the u here, but we'll highlight that one anyway. Okay, so if we replace everything here, we see we have -3 times the integral. That dx, we can replace that with 1 over 9 du. So we have 1 over 9 du. Divided by, we have the square root of 6 squared. You can leave it as 6 squared, but just for me, I always put it as a squared just to make sure everything is in the spot it's supposed to be. So we have a squared minus your 9x squared. We made that our u, so that's just your u squared. Okay, so that 1 over 9, we can go ahead and just factor that right out to the front. That gives us -3 times 1 over 9 times the integral of du over the square root of a squared minus u squared. Okay, so everything we did up here matches up because it gives us the very form we're looking for. Okay, so this -3 over 9, we can just make that -3 over 9. We can simplify it to -1/3. So we have -1/3. And this integral, we know that's equal to sine inverse of u over a plus c. So now all we have to do for our last step is replace u and a. So we have -1 over 3 times sine inverse, and that u over a, well, that's just 9x over 6. Okay, we knew our u and a right from the very beginning. Plus c. Okay, so if we just simplify, if you need to simplify in there, that's about it. But after that, you are done. So we have -1/3 times sine inverse, and 9 over 6 can be simplified to 3 over 2. So that's 3x over 2 plus c. And that would be our final answer. All right, so any questions on that one? Okay, now the thing is, like I said, I would put it into Newton as this one, but you could also see the answer as the negative of -1/3 of sine inverse, which would be cosine. So that would just be 1/3 cosine inverse of 3x over 2 plus c. Again, I wouldn't worry about that. I would just leave it in this form. But if you use like, if you want to double check your work and you use an app or something like that, it's possible this answer could come up. So all you have to do is take the negative of your answer, replace cosine with sine, boom, you have it. All right. Let's say if we wanted to find the integral of -2 divided by the square root of 100 minus 9t squared with respect to t. Okay, so just like before, you want to look at the form of the integral. And we see that it's similar to the integral of du over the square root of a squared minus u squared, which is equal to sine inverse of u over a plus c. Okay, so we want to rewrite your radicand in terms of squared functions and values. That means get that -2, move it out to the front, times the integral, that dt, I always just move it up top, divided by the square root of 100 minus 9t squared. We can rewrite that as -2 times the integral of dt divided by the square root. And that 100, we can make that 10 squared. 10 times 10 is 100. Minus, and that 9t squared, we can rewrite that as 3 times t, and that whole thing squared. Oops, move that down a little bit. Okay, so again, if you match it up to the formula, we can see that our a would equal 10. And if we match it up, we can see that our u is equal to 3t. Okay, so as soon as we find u, that means we can find du. So the derivative of u is equal to the derivative of 3t is just 3 with respect to t. So if we divide both sides by 3, we know that 1/3 du is equal to dt. And draw a little box around these to kind of separate them. Okay, so if we rewrite this, we have -2 times the integral. That dt, we can replace that with 1/3 du. So 1/3 du divided by the square root. That 10 squared, we know that's our a squared. So always just replace that back with a squared. And that 3t squared will give us our 9t squared. So we know that's going to be our u squared. Okay, and that 1/3, just going to factor that right out to the front. So we have -2 times 1/3, which is, I'll just write it as -2 times 1/3 for now, times the integral of du over the square root of a squared minus u squared. Okay, so we know that negative 2 times 1/3, that gives us negative 2/3. So bring that up a little bit. And that du over the square root of a squared minus u squared, we know that's going to give us sine inverse of u over a plus c. Oops. Okay, so now all we have to do is replace our u and a. So we have negative 2/3 times sine inverse of u over a. So that gives us, there is 3t divided by 10 plus c. And we don't have to simplify anything else, so that is our final answer. All right, any questions on that one? Okay. So what if we have the integral of 3 divided by 4 plus 100 x squared with respect to x? Okay, well, if we look at this one, it's really similar to the integral of du over a squared plus u squared. And we know that is equal to 1 over a times tangent inverse of u over a plus c. Okay, so we can take our original integral, we get that 3 and just factor it out to the front, times the integral, that dx, I just move it right up there, divided by, now that 4, remember, it has to be the sum of 2 squared terms. So that 4, we can just make that 2 squared. Plus 100x squared, we can just make that 10x, and that whole thing squared. Okay. So just matching it up to the formula, we know that that would make our a equal 2, and that would make our u equal 10x. Well, if u is equal to 10x, that means our derivative of u is equal to the derivative of 10x, which is just 10 with respect to x. So if we divide both sides by 10, we get 1 over 10 du is equal to dx. Okay, so as soon as you find your u, you can automatically find your du. Okay, so now we're going to bring down the 3 times the integral. That dx, we're going to replace it with 1 over 10 du. So we have 1 over 10 du divided by that 2 squared. We know that's our a squared plus u squared. All right, so that 1 over 10, we're going to go ahead and just factor that right out to the front. So that gives us 3 times 1 over 10 times the integral of du over a squared plus u squared. Okay, well, that 3 times 1 over 10, we can just rewrite that as 3 over 10. And this integral of du over a squared plus u squared, we know that is just 1 over a times tangent inverse of u over a plus c. Okay, so all we have to do now is replace u and a, and then simplify. Okay, so that gives us 3 over 10 times 1 over a, so that's times 1/2, times tangent inverse of u over a, so that's 10x divided by 2. Plus c. From there, we just simplify if it needs to be simplified. So we know here we can go ahead and multiply these two. Make that equal a little clearer than that. There we go. So 3 over 10 times 1/2 gives us 3 over 20 times tangent inverse. 10x divided by 2, we can just make that 5x plus c. All right, any questions on that one? All right. Okay, so let's say for this one, we want to evaluate the integral of negative. We have 1 divided by 5t times the square root of 25t squared minus 25 with respect to t. Make sure we fit the whole page in there. There we go. Okay, so if you notice this one, if you look at the form of this one, it's really similar to the integral of du over, and sometimes they'll have that absolute value and sometimes they won't. But either way, it's just the absolute value of u times the square root of u squared minus a squared. Oh, already have the du up there. Gotta move it up. And we know that's equal to 1 over a times secant inverse of u over a plus c. And go ahead and separate that. There we go. Okay. So again, if they don't have the absolute value around the 5t, that's no big deal. Okay, so we just have to rewrite our radicand terms. So again, that -1 constant, we'll move that out to the front. That dt, we'll just move that up top. So times the integral of dt divided by, we have 5t times the square root. That 25t squared, we can just rewrite that as 5t squared. And that minus 25, we can just rewrite that as minus 5 squared. Okay, so these two u values have to be the same, just like they're the same up here. And I'll show you how to fix it if it's not the same on the next example. But for here, both of these are the same, so we know that u is equal to 5t. And we know that a is equal to 5. Well, if u is equal to 5t, that means we know that the derivative of u is equal to the derivative of 5t, which is just 5 with respect to t. So if we divide both sides by 5, we get 1 over 5 du is equal to dt. Okay, so that means we can rewrite it as -1 times the integral. That dt, we can replace that with 1 over 5 du. And just to save time, we're going to factor that 1 over 5 right from the beginning. So factor that 1 over 5 right to the front. Divided by 5t, which is our u, times the square root of 5t squared, so that's u squared, minus 5 squared, so that's minus a squared. Okay, so we know that that's going to equal that -1 times 1 over 5, that's -1/5. And this integral, we know that's equal to 1 over a times secant inverse of u over a. Uh-oh. Don't need to put the plus c in there. Plus c. So now we just have to replace U and A. Which gives us, let me move it over to make sure we have enough room. So we have -1/5 times 1/A, so that's times 1/5, times secant inverse of U/A, so that's secant inverse of 5t/5. And clean up that 5 a little bit. There we go. Plus C. Okay, so once you replace your U and A, the only step left is to simplify it if needed. We go ahead and multiply those two. That gives us -1/25 times secant inverse of 5t divided by 5 is just t, plus c. Okay, so we have one more example for 5-7, but I don't know if we're going to get through. It takes about 2 pages to finish, and I don't know if we're going to finish that in the next, 11 minutes. So we'll wait and do that one tomorrow. So we'll finish up 5-7 and 6-1, and then we'll be completely done with the lectures. Okay, so if there are any questions, of course, feel free, hang back, ask away. If not, I will see you tomorrow. Make sure to start here. And hello.
I took an exam yesterday for Calc 1,
Mhm.
and it said it opens August 8th.
Why does they keep doing that?
I couldn't really take it.
All right. Those are what exam for.
Yeah.
Okay.
And then for
They do these things to me on
I
purpose.
know. And then for those final exam practice,
Mhm.
I know for Calc 2 it's like every one you complete is 1%
Mhm.
extra credit. Is that the same for this class?
For this one, I was thinking about doing that, but they kind of, because Calc 1 is any class that gives a departmental
Mhm.
exam,
Yeah, like
they
it's with
have,
them, right?
they have kind of say so over it.
Yeah.
But because with Calc 2,
Mhm.
we don't have to give a departmental
Yeah, exactly.
exam, so we can pretty much have a little bit
Yeah.
of, little more leeway.
Exactly.
So with that one, I have to check because they do limit the amount of extra credit we can get.
Right. Okay.
So that's the only drawback to
All
that
right.
one.
But
So,
just let me know, yeah.
all right.
Thank you.
You're welcome. Let me make a note of that. Uh-oh.